Hello and welcome to this lecture on fundamental computer organization and architecture. We will first focus on the concept of instruction set architecture and some of the considerations you need to take to design an ISA. We will in particular present the RISC-V ISA in some more detail. Next, we will focus on what is needed to implement parts of the RISC-V integer ISA, how it can be pipelined for increased performance, and what complications in terms of hazards that will bring. Finally, we review the memory hierarchy, including cache memories and virtual memory. When designing an instruction set architecture, or ISA for short, you need to consider multiple aspects like what is the internal storage of the processor, how are operands specified in instructions, and how many operands should they have, what type of operands and how large are they, how is memory addressed, what operations on operands should the processor support, how should control flow be expressed, and finally, how are instructions encoded? This picture illustrates some alternative ways to organize internal storage in a processor, all of which have been proposed and implemented throughout the history of computers. They differ in how internal storage is accessed and how many explicit arguments instructions can have. In a stack-based processor, example A, instructions operate on the top of the stack and therefore there are no explicit operands for instructions. Hardware-based stack machines, like Burroughs mainframes from the 60s, typically kept the top of the stack on the processor, and as the stack grows or shrinks, moves data to and from memory as needed. Today, stack machine abstractions can be found in the Java virtual machine and WebAssembly. Accumulator-based processor, like example B, were common when microprocessors were first introduced and still in some microcontrollers. In this model, there is one register, the accumulator. The accumulator is an implicit argument for most instructions, and the other operand is in memory. The register memory model, example C, is perhaps the most common model throughout the history. Here, there are multiple registers in the processor which can hold operands for instructions. The instructions can also operate directly on operands in memory. The x86 and AMD instruction set architectures are representatives of this model. Finally, with the introduction of RISC processors, a more pure ISA model were introduced in example D, the load store architecture. Here, instruction operands are always in registers, and you have to explicitly load data from memory to a register before being able to use it. And similarly, any result needs to be stored to memory. As you can see, the number of explicit operands varies, and we'll see some examples on the effect it has on the number of instructions and memory accesses. We'll investigate the same expression on all four ISA models. To the left, you can see the stack-based program representing the expression on top. Note that the push and pop instructions have a memory address as argument. Push A will read from memory location A and store the value on the top of the stack. Similarly, pop R will pop the value on the top of the stack and store it in memory at address R. Note that none of the arithmetic instructions have any operands. They are implicit on the top of the stack. To the right, we have a slightly improved code which reduces the number of instructions and memory operations. Here are the same situations for the accumulator machine. Every instruction is now also a memory operation, as one of the operands has to come from memory. The register memory machine further slightly reduces the number of instructions needed, and in particular the number of memory operations, as you can reduce the data loaded. For register machines, we require a bit of explanation. First of all instructions are assumed to be 32 bits, 4 bytes. This means that it's not possible to use a full address which takes 4 bytes in a 32-bit machine, plus an instruction with the register as operand within 32 bits. Therefore, we will first have to load a base address in register R10 and then load the other values specifying an offset from the base address. Here we have a summary of the effect of the different ISA alternatives. As expected, the stack machine code is most compact, and the register machine leads to fewer memory operations. Given that the register instructions are often easier to decode, this is the choice of any new ISA coming today, for instance RISC-V. AMD 64x86 is a representative ISA in the register memory class.